All right, welcome back. Today we'll talk about a few different things. I think toward the end we'll start talking about task switching. In between now and then, I guess we need to talk a little bit about the midterm, probably some questions about the homework, which was extended until Tuesday, right? And the midterm is on the 12th of October. And whatever else. So first though, tonight at 11:30 Chicago time, there's this presentation by Elon Musk of SpaceX. It's the second presentation in a series. He's talking about how they are going to start a base on Mars. 11:30 tonight. You better believe I'll be watching it.
Local time 11:30 or Pacific time 11:30?
This local time, yeah. Incredible work they're doing. If you haven't heard about SpaceX, it's time you did, because they will change everything if they manage. All right. All right. Let's start with questions on the homework. Who finished it? That's not finished it, but it's kudos to you. You started it. It's good.
It works. It's just that I was going to come talk to you. It's a very weird error in which if I run the programs one after the other, the pointer which is returned to the function itself is wrong, even though at the end of my functions the pointer is the correct pointer, and it reaches the function which called and not the address is wrong. Doesn't matter in which order I call them, but in the next program it happens. It's weird.
All right. So I don't have the full context, but I can think of a couple of common errors that people would make. One would be to use a global variable to manage your the mmap base, like where you start mapping things. It really should be one per process, right? Every process has its own layout. That's one. Another one is types. So it's possible, perhaps, that you're returning a 4-bit value, 32-bit value instead of a 64-bit value, and there's some garbage in the register at the 64-bit level, like at the upper 4 bytes. Seems a little unlikely in this case. Generally, the best way to proceed is to use GDB. Every step along the way, look at what's in the registers. Even after you leave your sysmmap, you might want to see what's happening when you get to syscall, when you get to trap, and then trap ret as the values are. Probably, by the time you're at trap ret, when it's popping RAX, it's already the wrong value. It is extremely unlikely that you would go from trap ret with the right value and then hit the iret queue and then suddenly have the wrong value. It just doesn't really happen. So probably you can find the error somewhere in between there. There were a couple of curious little bugs, and maybe we'll take a quick look at that. Let's see. The wrong document. Here it is. No. Oh. My VMware license expired. I'm there. I'm back. Sorry? For the Linux machine, yeah. And so right, okay. So now this is unmounted. Okay. Almost there. All right. So as a reminder, if you're interested, I think it's pretty cute the way it works. If you just say make print on the command line here, that's what generates this whole PDF file. It's a really cool little build system for that, and we'll have no use for it in this class, obviously, but it's the sort of thing you don't usually run into. It's really good stuff. All right, we were going to look at a couple of weird bugs. One was One was the sysmap had an int return value. And it turned out it doesn't matter. And that was a little curious. So the return value from sysmap should be a pointer. It could be any kind of pointer you like, as long as it's 64 bits, and every pointer will be. Or I like to write it as adder t. In fact, if we go look at, let's see if it's actually right in syscall. It may not have been fixed before I printed it. Ah, yes, look at all this. That's terrible. So most of these are fine, because they're actually not returning pointers. So it's not going to give you much of a problem. In fact, I think none of them return a pointer. So it's not so bad. But I added another one, what was called sysmap. And here it was declared, as it should, with a 64-bit return value. But then in the template for the sysmap inside of proc, it was with an int. So now you would think that, oh, it's an int, so it's only going to return 4 bytes out of your address. And your address is 8 bytes. Right? So those lower 4 bytes are all zeros. That's really weird. Like, now we're just returning a 0 pointer, and clearly that's going to screw everything up. In fact, it turned out that the way the GCC compiles this, it doesn't actually do that casting. It just returns whatever value you provide. So if you put a value let's see, if you say return some value, it puts that in RAX. It doesn't care that it should be a 32-bit value, at least in the cases that I saw it. That seems like it's probably okay to do it on the return side, as long as you handle on the calling side, you handle the value there. Right? Probably that's what GCC is doing. To be clear, if it says int, you really should only be getting 4 bytes. Right? You shouldn't be getting an 8-byte value. So it needs to somewhere shave off those top 4 bytes of your value. So you can do it on the return by setting all the higher bytes in RAX to 0. Or you can do it on the call, like after you get your return value from calling a function. You make sure you only use the lower 4 bytes, and I think that's what GCC did. So, it was a typo more than a bug, because it doesn't actually affect anything, but it still looked a little worrying. The other thing that was really interesting was here. In trap, here. So I'm sure you've all run into this printout a whole lot. Usually trap 14. It says which process, it has a name for the process, this is all good, which CPU. This one is also fine, that's usually a small value. If you're, since we're in user space, and we're using really small programs, and we're always starting at 0, it's going to be something like 60 or 80 or small values like that. So that's all fine. But then the address here, that's also usually fine, because we usually use small values, except with the mmap. Because with the mmap, we have a really high address. Right? We're not dealing with a heap, which is way under 4 gigabytes. It's like way down there. The stack as well, but the mmap, that's sitting up at a quarter of the entire address space. So that actually needs to use those 48, 64 bits of address. And here we're saying print the address with an X, and the X is a 32-bit print. So we get just the lower 4 bytes. So it looks like when you get one of these trap error messages, it'll say, oh, the address that I was trying to access improperly was 0 something. Right? It won't have that 4 in the beginning. So if you change that to a P, and I also push something up, then it'll print out the full stack. So not much of a bug, but pretty confusing. If you think, oh, did I return a 0 pointer? What happened? Right? I just returned the 4 pointer, and still it comes out 0 in the error. What's going on? So I thought that was kind of a sneaky one. Anyway, it's something worth watching out for. I think if you're using if you're using the built-in printf with GCC, this is C printf. This is a special printf from that comes with XP6, right? In fact, when you build it, it says -- no built-ins, something like that, in the makefile. But if you use the built-in printf, then they actually have a specially like hard-coded version of printf that reads the format string. The compiler knows about the format string. Now this is really very unusual. Usually the format string is just a string. The compiler would have no idea what the string means. It doesn't care. Right? But for printf in GCC, it does care. And it sees D, that's a 32-bit integer. Right? And then it looks at the parameter here, the PID. Oh, that's also a 32-bit integer. That's fine. And then it gets to here. Oh, print out a 32-bit value. Aha, but the address is a 64-bit value. So now it'll give you a warning saying type mismatch something or other. So you'll see that sometimes with printf, but you will not see it with C printf. And not with the printf in XP6 anywhere, but in other cases we'd see. All right, you had some time to think about homework questions. Yeah?
So after I got done for your office hours were done, I went home and I started messing around with trying to figure out what's going on with the issue again.
That issue, which issue is this?
The one about trap 14, because after I debugged it with GDB and everything, I saw that the address was there, like we saw, you actually did it too.
All right, so you had the right mmap address.
Yes.
Okay.
But I'm guessing that because of the warning that I have the implicit declaration for map pages. I'm guessing that I'm not actually mapping anything into address.
Ooh, that's not really the case. But this was a good question that showed up on Piazza too, I think. So what's going on with this map pages, right? If we implement our sys mmap in the proc.c, we want to use map pages. If we want to use map pages inside of proc.c, which we don't have to, but if we do, then we have a bit of a problem because map pages is not declared inside of there. There's no include file you can include to get the correct profile, correct signature of map pages. So there's a couple of things you could do. First, you could just ignore it. The compiler is just a warning. It's not a big deal. So now the compiler will assume that there will exist a symbol map pages somewhere at some point. And it probably will return an int. It'll probably accept some integers as argument. Forget about it. And that's actually fine. So what happens then is it generates an object file. Let's take a look, because this is good stuff to know. I'll try to answer your question toward the end of the long segue here, or long detour. Let's take a look at, why don't we do, well, we can't do proc. Why not? Proc.o. See what's in it. Okay, so here, what happens is you get a bunch of these relocation entries. Actually, this one kind of not that nice. Yeah, are these better? Debug info. Let's not have that. Okay, this is good. So you get this. This is the object file, right? I just said readelf -a. It reads out all the sort of metadata that's in this .o file. From the top, it's just the regular headers. It says, okay, there's this much text, right, this much code in the file. It should be loaded this way, right? You should put the stuff starting from here, going until there, should go to this virtual address space, or these addresses in memory, and then you should put all of this stuff in there, and so on. That's how you load an executable. We can see it in exec. It basically reads these things. Okay, and later on, there's some, actually, this is an object file. It's not a binary yet. So it has some sections in it. It doesn't say where it should go in memory yet because it hasn't been linked. And then comes all these relocation entries, or yeah, that's what they're called. So here it says, oh, this far into my code, at number 22, there was something where I don't know what to put there. Like someone's referring to map pages. I don't know what map pages is. Right? And so here, someone was referring to ptable. Ptable isn't there in proc.c. It's somewhere else. Someone's referring to acquire. That's in spinlock. Right? These symbols are in other object files. So when this gets compiled, you're only compiling proc.c, and you don't see anything else. The compiler doesn't know that there are other files. So it's making this object file without knowing what other functions are there. So it just says, okay, it's going to be this acquire thing. When you find it, please put the address here, at address 57 into offset 57 into the file. Oh, and by the way, it should be a 64-bit address. It's not always 64-bit. Sometimes it can be relative values and sort of thing. But basically, stick 64 bits of address into this place when you find the symbol. So what happens now when you say map pages? The compiler does the same thing. It just leaves a relocation entry saying map pages when you find it, and then the linker puts all the files together that you say. You say, like, oh, I want to link my executable. Take these .o files, make an executable out of it. If for every relocation entry in all those objects there exists a symbol in some other file, then it's happy. Linker is happy. Otherwise, it says undefined symbol, right? And you'll have to link with some more objects, or maybe you forgot, you have a typo or something like that, right? Right. So now, when you link vm.c that has the map pages and proc.c that wants the map pages, a linker sees, okay, that's a good match. Let me put the correct offset in there, correct address, and then we're good to go. So the linker doesn't do anything about types. The compiler sort of does a little bit about types, because it assumes, if you haven't told it what kind of values it takes, it assumes that you're passing it some type. And I actually don't know what the assumed types are. Usually it says, like, oh, implicit blah, assuming integer return value or something like that. So it's possible that sometimes you get weird behaviors, because when the compiler tries to pass values into this unknown function, it might put them in the wrong place or have the wrong size of the values and such. And it might give you lots of warnings saying, oh, you're trying to put in a character here, it should be an integer, whereas in fact it should be a character. It just didn't know it was supposed to be a character. Right? So the correct way to fix this, several different ways. Okay, one was to just ignore it. That's not really correct. The next one is you declare it. All right. So what's a good way to declare it? You take map pages, copy this stuff. In fact, it's not quite going to do it. You'll have to, well, if the static is still there, I don't think it is. I think I removed it for the template.
Yeah,
right. Because otherwise, the linker wouldn't even find it. Right? Static means put some garbage before the map pages symbol. So it'll say blah, 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 underscore map pages. And then when you try to link it, if someone else typed map pages, it doesn't match up with blah, blah, blah map pages. That's all static does. But it's pretty convenient sometimes, because you avoid this confusion of this symbol looking like it should be here, but it shouldn't. Or maybe you want to have lots of different, in every C file of yours, you want to have a symbol called test, because you want to be able to call the test thing from wherever you are in your function, in your object, but it should be a different one in every file. Well, if you call it static test, there won't be any multiple definition linker error. Right? So that makes sense too. In this case, I removed it to make life a little easier for you. Okay, but it's not quite there yet, because now we still haven't declared it. So what you do is you copy this part of it, and you stick that with a semicolon above where you use it in your proc. Right? That's kind of an ugly way to do it, but it'll work just fine. So now it's available in proc.c. It's not available anywhere else. Available in the sense that the compiler knows that this should be a pointer, this should be a 64-bit size, and so on. Right? And finally, the last thing you can do is you can put that same line in defs.h. And defs.h is all those public symbols that are declared. So now it's going to be available in every file because they all import defs.c, and that is probably a slightly better solution. But of course, map pages wasn't meant to be used from outside of vm.c. So yet another way to do it would be to have the stuff that does the mapping, right? The stuff that maps are, let's see, stuff that increments the mmap base, right? The stuff that maps a bunch of pages for this particular mmap call, and maybe some other pieces too. All of that can just go inside of vm.c. And that, I think, would be the cleanest solution. So you say, like, alloc mmap. Make one of those in vm.c, and you call that from proc. Of course, that won't be available from proc, right? The compiler doesn't know about it, but you put that one in defs.h, because that's like a nice public interface that you might want to be sharing. So that's probably the cleanest solution. Right. But and then you should do the part that reads in from file separately, because reading from the file, that doesn't belong in vm.c, probably. Okay. That answer your question? Yeah. Cool. Other questions? All right. So, as you've noticed, oh, in fact, let's see what the outcome is here. All right. I think A was yes. Yeah. I'll come along. It seems pretty awesome. I wouldn't want to live there. But I think just going for a few months or a year, help out with the colonization effort, awesome. It looks like it's happening. The question is it happening when we are still, ready to go? But we'll see. Okay, so right. So the course, as you know, is very much focused on doing these big projects, learning the code, and understanding what's going on in the whole OS. My philosophy is that if you understand x86, you understand almost any OS. I mean, there's some operating systems that have a very different design. They're not generally that popular. But for a classical OS design, x86 is an excellent prototype, and Windows isn't going to be very different. Mac OS is almost identical. There's a little bit of extra layers in between. Maybe Linux is pretty much exactly that, except it's enormous, right? And all of the little real-time OSs that you have in embedded systems and so on, like probably 100 different operating systems, all look like x86, one way or another. So it makes sense to just learn the code, because if you learn the code, you understand operating systems. So that's the main sort of advice I can offer for studying for exams. When we're dealing with a particular piece of the OS, so now we're doing mmap. Right? Now the best way to learn, I think, to really get settled in, get your knowledge settled, is to look at all the other sort of auxiliary functions and make sure you understand what they're doing and why. If you feel a little unsure about it, ask a question on Piazza, come to office hours, Google for it. x86 is a relatively popular OS for teaching, so there's a lot of discussion online. Read the textbook. There's ways to figure it out. If you can't figure out what's going on, this is a very simple OS. You really ought to come and ask about it, or ask in class, right? Because it's about as simple as you can make it. So sometimes it's hard to know if you understand it. Like for yourself, it's hard to know if you understand it. And I think that's where a homework comes in pretty nicely. If you can't get it to work, you're struggling to understand it. So at least it's better than just reading a textbook and say, yeah, I get this. Right? It's good to do some exercises. That said, I thought we would take a quick look at one homework question, one question from the exam. This was from a final some years back, and do a few clicker answers. Right? In fact, I'll record this just for, I don't know why. Let's do it. So I don't think this question is going to appear again, but there's certainly going to be questions very much like this later on. So this is one out of, no, it's not actually 7 pages. There's one front page. So there's 6 pages that are somewhat like this. Most questions are short answer, absolutely no essays. We all hate reading essays. Whoever is helping to grade hate reading the essays. And generally you can see like, oh, there's one point here that does not justify 100 words and writing on the back of the page. Almost all are short answers. There's very rarely a multiple choice sort of question. Usually it doesn't help you much to memorize, I don't know, tables of things. It's not like that. What you do want to do is try to remember sort of the structure of the operating system. Like, where are the stuff, like where can I find map pages? Okay, you can look that up, but if you know that it belongs in vm.c, that might help you a little bit. If you know that it's like part of the virtual memory management, that sort of thing. So being a little familiar with the code is going to help also in the exam. You're expected to bring the book for the exam. You won't need it for now, I think. We're skipping 1 or 2 of these sub-questions. And you can write anything you want in the booklet. Right, so why don't we get started? We'll start with the first question. And I have some, here, midterm question A. Those are the, so it's, oops. So it's not going to be multiple choice during the exam. That makes it a whole lot harder, right? But we'll do it that way now. So what's the maximum number of pages that can be represented in a page table? And here, because this is a couple years old, it says the union of the page directory and the individual page tables. But we have 4 levels now, right? The PML4, the PDPT, the page directory, and the page table. So it's always the case. There's no point in trying to do the multiplication of 2 times 2 times 2 times 2 times. You can write it any way you want as long as it produces the right answer with numbers. All right, we have 5 answers, 6, 7. All right, let's see how many are here. Actually, if you have a clicker, can you hold your hand up? Okay, well, pretty good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did you have one? No, 9. All right. All right. Well, it must be 10, at least. All right, good. So let's see what happened. Okay, very good. We have something to work on here. Right. So the number of pages. 1 page represents 4,096 bytes of memory. So if the maximum number of pages was 1,024, that would be 4 megabytes maximum RAM in the machine. Or maximum, not RAM, virtual memory. And we have more range than that. In fact, we have more than 16 megabytes of virtual memory as well, so we can leave this one. Okay, so this is getting pretty close, right? The argument here is probably that in each level of the page table structure, there's 512 entries, right? Now there's the PML4 that points at a PDPT table, right? PDP table, and then that points at a page directory table, and then that points at a page table, which in turn points at pages. So it's 4 levels, and there's only 3 there, so that can't be it either. This one here, 512 is 2 to the power of 9. So multiply 4 of those, that's 2 to the power of 36. So the correct answer would also have been times 512, that's exactly the same thing. Okay. Any questions on that? So let's do the next one. Let's see. Oh. Right, how does the CPU know which page table to use? So this is not how does the kernel know. This is the hardware at, when the program makes a memory dereference, how does the hardware figure out which page table it should be looking up that address in? Okay, still waiting for one more answer. Nope. Someone didn't answer. All right, well, that didn't help. Okay, I will stop it now. Oh, there it is. Okay, so those were the results. Pretty good. So the CR3 is the correct answer. The control register 3. When you're switching to a new process, you put the address of that process's page, PML4 really, in the CR3 register, and now the processor knows what to look at. In the exam, you wouldn't have to answer CR3. It'd be enough to answer a special register, right? Or something like that. That indicates you know that there's a register in the CPU that keeps the address. This is for the OS. The kernel keeps track of which page directory, PML4 is actually what it's pointing at here, which page directory this process should be using, but it doesn't mean that that's the one we're using right now. But anytime you switch processes, and hopefully we'll get to that toward the end of the day, when you assign this variable to be the current process, then at the same time you read this and store it in CR3 so that there isn't any confusion. This is actually a very special variable here. It sounds weird when I say assign that to be the current process, because if you have more than one core, you can run more than one process at the same time. So you can't have a global variable that stores the current process. It just doesn't work. There's some special magic. It's a thread local variable. We can look at how the assembly works, but it's actually using the segment registers to create these thread local variables. It's a neat trick. Okay, and this global descriptor table, that's the one that describes the segments. Right? It has nothing to do really with the page table. And the proc variable is which one is the current process. But again, the CPU doesn't know about variables. Variables don't exist to CPUs. There's addresses, that's it, and the contents of those addresses. Doesn't know about types and such. Okay, so question C. So why would a tiny little program have a huge page table? Oh, no answers yet. These are the answers we can choose from. So most of our programs, they would use probably 3 entries for its virtual memory, for the basic virtual memory layout. Like there's the code, there's the stack, maybe it's using heap. And I think there's an invalid entry between the stack and the code to make sure you don't overwrite the code with stack values. But that's just 3 or 4, so what's going on? Okay, we're getting there. we're choosing among these, right? 10, very good. Wow. Okay. Yeah, good. I'm glad this one was a little tricky because I kind of there's a it's sort of a trick question. Only because I gave 2 answers that are actually correct. So these 2 are the correct answers. The kernel code does not require 50,000 entries. That is what is that? 200 megabytes worth of memory, and we have 4,000 lines of code. There would be a very inefficient compiler to grow it that much. So it's not the kernel code. That means not A. The heap. It is possible for some programs to use that much memory. It's no problem. You just raise the break by 200 megabytes, and there you are. Now you would need that many entries. But most programs don't do that. Like a normal small program like cat probably wouldn't even allocate any heap memory. So it's not the heap. For the rest, we have this mapping. If you look at the entire address space again, at the bottom we have a tiny little bit. And then at kern base we have the text. Okay, that's probably several pages worth. And after that, well, we have that whole flat mapping. We have to map all the physical RAM into the page table. And that was, well, the fist top is 224 mega, if I remember correctly. And so in order to fit that, well, then we do actually need 50,000 entries, about. You could do it a different way. You could use those huge pages. x86 doesn't do that. It's just doing 1 page at a time. But you could conceivably map, say, a gigabyte in one fell swoop, right, with one huge page entry somewhere in the page table. Okay, let's take one more. Oh, there's more than one more. I'll close this. All right, so next question was here. You wouldn't want a user program to be able to read kernel data structures because there could be secrets in there. But we do have this whole flat mapping. Like every process has this mapped in. So why can't the process then just go and read it, assuming it knew the address of the data structure it's interested in? Why can't it just go and read that if it's mapped in anyway? Couple more. Yes. All right. Okay. We have a plurality is winning. This is right. So in the page table, there's a flag that says this can only be read by supervisor, or this can be read by users and supervisors. So that's the US bit, U/S bit. The A bit is accessed. Right? That's the one we talked about last time. It says someone read from this page recently. Okay, the segment register, there isn't one. I mean, there's multiple, that is. So the CS, DS, ES, FSGS, those are the segment registers, and they don't actually have much to do with this. Although one could imagine, now in 64-bit at least this is not the case, but in 32-bit protected mode, the segment descriptors, they have a limit. So you can say, like, this segment goes from address 0 up to kern base, and no more. And so now if you set your segment or your data segment and your code segment registers to point at the correct segment descriptors, now those could also block the user from, or user programs from reading kernel memory. So now there would be an actual segmentation fault as opposed to a page fault. Maybe that's the origin of the term, right? The kernel will still call it a segmentation fault because that's just sort of the convention now. But, so that's another way you could do it in 32-bit mode. In 64-bit, the segments don't have that much purpose. And in particular, the base, like where does the segment begin, and the limit, how far does it go, neither of those are used. They're supposed to be 0. So segments really wouldn't help that much. Memory encryption is, it's not right, but if you didn't have page protection, maybe you could imagine doing something like this. Problem, I think, is you would have to be able to encrypt everything. All right. So now if you, like when you come back to the kernel, how do you decrypt it? Like the key would have to be available to the kernel but not to the user program. So now that's hiding somewhere, and without protection, I don't think you could do it. So I don't think there's really a good solution there. But there will be situations where maybe it's warranted to do encryption of main memory, and one of those might be where there's sort of spy devices involved. If you're very worried about the contents of your memory being visible to not to other software, but to someone who has kind of attached things to your computer, this could help. Okay, and then antivirus software is just sometimes you want to add something weird. So, I'm told those are called distractor answers, and they're supposed to be important, but some of them are bad, and others are closer to the truth. I'm still trying to learn that. Okay. F. So if we wanted, we could just, when we switch to a user process, and I'll just start this again. When we switch to a new process, we could just not let the process have this mapping, right? Make the page table only be the user part, nothing in the kernel side. That will create some problems. I think I am not completely sure how you handle the system call, because in your trap vector you need to have an address. You have to say that jump to this address, but if it's not mapped in, you can't really jump to it. So you'd have to have at least a little bit of kernel code available to the user process. But you could hide most of it, let's say. So once you get into the kernel, you switch to a page table that has the kernel data structures, and then when you go back to the user program, you switch away again. So now you're essentially not showing anything to the user program. But then there's at least one thing where one case where the kernel will need to access user space memory. So if you say, read from disk into this buffer, or here's a file name, right? Open it for me. The kernel needs to be able to read what the user program puts somewhere. And the user program can only put it in its own memory. So the string will actually be in user memory during the system call. So now how can the kernel read from the user memory if it doesn't have that mapping? So if you have a kernel-only page table for the kernel, a user-only, essentially, for the user, now how does the kernel read from the user's memory? So This is very hard to have in a multiple choice question without revealing the entire answer. So these are sort of like just hints at the direction, like one of these things you might want to use in your solution, but you can't, it doesn't, that's not the solution itself. It's looking very even so far. One remaining. There it is. Okay, wow. Okay, so that one we need to discuss a little bit. Let's take it from the top. A, use V2P address. So you're given a virtual memory address in the user's address space. Call it 100. You know, the user will have small addresses. So it's something like 100 or 1,000, something like that. And now we use V2P on it. What is that? What does V2P do? It's a macro.
Minus current base.
Minus current base. So current base is extremely large. So now we get a very negative value. And then what? And then nothing. It doesn't do anything for us. The point of the V2P macro is to take a kernel virtual address, part of the flat mapping, just get the physical memory address that corresponds to this. And the only reason to use it really is when you want to map in a new physical memory page into someone's page table. Right? You need to be able to tell this map pages, this is the physical page. I can't remember any other case where we, at least under normal circumstances, where we would want to know the physical address of a page. It's kind of pointless because every time we dereference or we reference memory, we're always talking about virtual addresses. Yeah, all of the rest are basically when you deal with page tables. When setting up page tables, we need to know the physical address. All right, the same applies to this, P to V. So here we have, actually, a little bit less. We'll skip that one for now. Read. Read is for reading from files. Read is a system call for reading stuff from files, not just from disk, but from various kinds of open files. Right? So you say read file descriptor into this buffer. Well, now we want to read something from memory. That's not going to work. Okay, so if we knew the physical memory address that we're interested in, we don't, right? Because we're provided a virtual memory address. But if we knew the physical memory address, then we could use P2V and read from our direct mapping. Right? So now the remaining part then is how do we get the physical memory address given a virtual memory address? That's B. So walk page directory takes a page table parameter and an address, virtual memory address. Right? So now we say we know which process we're running. So with walk page directory, we give it the process that we're interested in, right? Its page table, say the virtual memory address, and back comes a page table entry, which actually has the physical memory address in it. Right? Page table entry is the physical memory address, but the lower 12 bits are some permission flags and things. So we add that out, mask out the lower bits, and now we have the offset of the address, the physical memory offset of that page, and then we take the lower 12 bits from the actual address, put those in there. Now we know exactly which physical memory address. And then finally, we add current base to it. And now we can read from that place, and it will have the contents that we were interested in. So we can manually do the page translation by following the page table ourselves. But that's the only way to know. Like for one virtual memory address, what's the physical memory address? The page table is the directory, the dictionary that tells us this. Questions on that? Okay. Right. So there was a couple of other questions, and we can't do those multiple choice. But I thought I'd point out how they work too. Oh yeah, so this one here, in this case, it might be much faster and easier to answer the question with just a line number. So if you know where this thing happens in the code, you just write down the line number and we're set. And here, when handling a system call, the kernel is accessing this user space memory. But where does that actually happen? So now there's some place. Actually, I think this was a pretty bad question because there's multiple places where this actually happens. But now you dig up one place where you know that the kernel is accessing something in user space. So it could be a string parameter on the stack. It could be a buffer that's passed in. So if it's a string parameter, what could take a string parameter? Exec could do it. Open could do it, right? If it's a write, then the buffer it will be in user space. So now you have to find where was this buffer used in the kernel. Where do they actually read from that buffer or write to that buffer in the kernel? Right? Just provide a line number. So you see, you cannot answer a question like that without knowing sort of how the kernel works. The answer is extremely simple. It's 4 digits, right? But you can't calculate it really. You have to know how the whole thing works, so you can easily look it up. Like, okay, right, there it is. So there's going to be several questions like that. Any other questions on the exam structure sort of thing? Typically, the median is about 50% on the exams, and the mean as well. There's always someone that gets the full score or very close to the full score, but I wouldn't expect most people to get that. I would hope that most people get around 50%. Or better, of course. Okay, so if we're done with all this, let's talk a little bit about processes then. I think, yeah, we started talking about this init proc a couple lectures ago. We'll go back to that briefly. Right, so let's see, in main.c, user init. Oh. Here it is. Okay, in proc. Okay, so you may recognize this. Right. Main, toward the end of main, when we're almost done with everything, we call this user init thing. We put a little bit of code in the bottom. So we allocate some user virtual memory, one page at the very bottom. We copy in a little bit of code in a magic way that isn't so important. We set up the register contents to make it look like this was a process. Like we have this strat frame that we're kind of manually populating with values as if we came in from a process in a system call. And then finally, toward the end, we say, oh, and this process here is a runnable process. So next time you get a chance, continue running it, please. Right? Except it never ran before, but that doesn't matter. We're saying here, next time when you return in our strat ret, right, when we return from this process, next time we should continue running at address 0, I suppose that's about it. All right. So from there, we are then running this code, sys init. No, it's called init code, which calls sys exec on this function, on this program init. So now it starts running init. Right, we have our system calls. At some point, init, which we can skip for now, starts a new process. It forks and it starts it's xxsh. So now we have two processes. So now the question is, how does this all work? When you have more than one process, so far one process seems pretty straightforward. We go in and out of the process. We're switching to the kernel, and then we go back with all the values back in the registers and start running the user program again. So I think we've sort of settled how we switch between user mode and the kernel and supervisor mode. But what does it mean to switch between processes? That's sort of the remaining question here. So you have a few different processes running. At some point, well, there's several different things that could trigger a switch between processes. The most common one is a timer interrupt. In a preemptive kernel like this, a timer goes off 10 times, 100 times, sometimes 1,000 times per second, depending on just kernel settings. And when the timer goes off, most of the time, the kernel decides, okay, well, I'll run something different, right? And that's a context switch. So I think we're gonna need some drawings to get this right. And this is really tricky stuff. So we'll do it another time. I think one more time next lecture. But let's give it a shot now. So we'll call this the user stack. And I think most of you are familiar with how a stack works. Right? So in every stack, there's a bunch of frames. I call it sometimes activation record. It's the same thing as a stack frame. And there will be a bunch of those. Oh. And it grows down like this, right? And so your RSP is always pointing over here to the bottom of the stack. It's growing downward. And inside of this activation record are a few things. You have your function parameters, sometimes, not usually for a 64-bit, when it's compiled 64-bit code, but for long parameters, or if it's a struct by value sort of thing passed. In general, if it doesn't fit in your registers, it'll go on the stack. Okay, so what do we have? I should write this. So what's in the stack? We have some parameters. We have local variables. Does anyone remember what else might be in there? There will be some stored register values, like temporary storage, which isn't declared as local variables in your C program, but sometimes you want to call a function, and you know this function is going to overwrite all your registers. You'll stick the register values away on the stack for now until you come back from the function call. There's one more thing that's really important. There's really two things that are on there. One more thing that's really important that's always on the stack. What's that? Return address, right. And then there's something called a base pointer. So the base pointer, that's your EBP value or RBP value, that points at the beginning, like just before the previous stack frame, and your ESP is pointing at the top. Anyway, so whenever you make a function call, you get some of this stuff in a new activation frame, and it keeps growing down like that. All right, but now a timer interrupt goes off. So we actually have another stack that belongs to this process. We call it the kernel stack, and it's initially empty. Which stack where the kernel stack is, that's stored in that trap switch segment. Perhaps you recall there's this big structure, but the only thing we use is the RSP entry. We stick it in there. And there was another thing. If you use a syscall register, it's stored somewhere else in the MSR underscore star register, right? I think it was there. Or was that just the segments? That may have been just the segment values, yeah. Anyway, so it's stored somewhere before you go to user land. When you return from an interrupt, before you go back to user space, you tell it, like, next time an interrupt or a system call goes off, go and use this kernel stack, because we use a different one for every process. All right, so when the interrupt goes off, or the system call, as the case may be, now we suddenly get start growing our kernel stack. So there'll be some things here. There'll be the RIP, there'll be the RSP. These things are stored by the hardware. You had your E flags. Some things like this ends up on the stack. And then we're in all traps. All right. By the time we're there, okay, now we're going to put the rest of our trap frame on here. So we can call this a trap frame. All right. It's relatively long. We have all of our register contents in the trap frame. That all went on the kernel stack. Okay. So now after that, it's the normal thing. So now we're calling main, all right? And from main, let's see, what were we talking about here? Yes, we're going to get and we're not calling main, sorry, we're calling trap. It's the trap stack frame. And inside of trap, actually we should go take a look at that now. We end up here. So now the stack looks like this because we're in the trap function. So this is a trap stack frame. Trap frame is sitting above there because that's what was created by the trap ASM. And then this pointer here is actually sitting in a register. Because this is just a pointer. It'll be in the RSI register, the first parameter passing register. But it's pointing to there. Okay, so we come in here and we see, oh, it wasn't a system call. In fact, it was a timer interrupt. So we increase this ticks value, and then we're done with that. Unless this wake up here, unless someone's waiting for a certain tick. And this is if we have a, could that be a sort of sleep situation? I didn't think we have alarms supported, so I'm not sure what it's doing. And we'll see what the sleep and wake up, how that works later. Okay, so it's none of this stuff. It's not the default anymore. Okay, so down here. If we have a current process, here. If we have a current process, we don't always. We could be in the process of deciding which process to run next. So our proc value is null. But if we were about to choose a different process, and if that process was running, and if this was a timer interrupt, then we yield the CPU. So, all right. Let's add this on here. There's not going to be that much in this trap frame, right? Because, well, it doesn't take any parameters. And even if it did, those would probably go on the registers. Let's take a look at what yield does. Okay. Not a whole lot of local variables. So it's a very small trap frame. Very small stack frame. Okay, so we change our state to runnable. This is pretty good because this process is going to yield the CPU. So that's good. Now we are no longer running, right? Except we're actually still running. We didn't change the execution at all here. We just said, in principle, this process should not be running anymore, but we're still running. And we call this function sked. You want to watch out because now it's starting to get a little hairy. So let's put that in here. right. Okay, we can actually ignore all of this. This is just some error checking. And then we get to switch. So sched, the purpose of sched is to switch to the scheduler. Scheduler is this infinite loop. It just goes around looking in a p-table array to see, is the next process runnable? If so, start running it. That's all it does. That's what we want to switch to. In some weird way, that one is kind of running. The scheduler is sort of running. And we're in the middle of that loop somewhere. And we want to just get back to wherever we were, continue running the loop, find the next process to run. But we want to stop running our current process. Okay. So we call this switch function. I should have made this a little thinner, I think. Do it now. This program, by the way, is called OmniGraffle. It's awesome for making figures. Let's just say switch. And I usually make prettier figures if I'm not doing it live. All right. Let's go take a look at switch. So what we're saying here is, let's switch from the current context, whatever that is, to the scheduler context. Okay? In fact, we're not going to return from this function. Not just now, at least. So let's go take a look at switch. Ooh. All right. So now we're pushing a bunch of registers onto the stack. And then we switch stacks. So in RSI, let's see, I got it wrong. RDI is the first parameter, RSI is the second parameter. So we're saying, store our current stack register value, like the pointer to our current stack. Store that in whatever the first parameter is pointing at. Let's go back here. The first parameter is our proc context. So we're basically saying, let's point this proc context at our current stack. Remember where our stack was. And then we change it over to whatever this was pointing at. So this, presumably, is pointing at the scheduler's stack. Let's go back. Oh. All right, so on our current stack, we store a bunch of callee save registers. Half the registers are the responsibility of the calling function to store. So if it needed whatever values was in those registers, it would have already stored those on the stack before it called this function. But callee, that's whoever gets called, it's our responsibility to store those registers if we need it for later. Or no, the other way around. If we're going to use those registers, we have to store the values and restore them before we return from our function, because the calling function doesn't expect us to overwrite those 6 values, those 6 registers. Are they 6? No, they're 7. All right, so now we're switching the stack, and now we start popping a bunch of registers. What's happening there? I just switched to some other stack pointer. In fact, that one was probably created the same way. That stack just called this previously. So I'm getting whatever the other stack has, a bunch of registers. I'm getting those values into my current registers. And then we're just returning. Oh, and why does it say that? What? But why is there a question mark? Maybe the question mark is, should it be a ret queue? But it doesn't matter because it's a void function. It doesn't have a return value, so it doesn't matter. So anyway, now we return to wherever we came from, but where did we come from? Yes, we return to wherever it says on the other stack we should return. So in fact, we come from sked into switch, but we return from switch into, let's see. Here we are. There. This is the scheduler loop. It goes around here, finds a process that is runnable, makes it running, and then switches from the scheduler into that process. Right? And then when that process is done, when that process calls switch, we're returning out of that process, so to speak. Out of switch, we return back in here. So it's the same it's one piece of execution, but we're not returning to the right place. So let's just continue as we have a few more minutes. Let's go around the loop. This one here says, okay, let's use the kernel's page table. The kernel has a page table without any user memory in it. And we say, oh, we don't have a running process anymore. So we set that to 0, and we go around. Now we start looking in the page table. Is there one that's runnable? Once we hit one that's runnable, we said, oh, this is our current process. This sets the page table, so basically sets the CR3 to point at our arrow PG-dir, or Peter. Is it PG-dir?
PG-dir.
Yeah. Okay, so now it's running, we say. Well, it's not quite running yet, right? Because we're running the scheduler. But now with the switch here, we come into switch, ask the scheduler, put the scheduler's register values onto the stack, switch to a different stack, load the old values from the process, and then return back into the process. So when we return back into the process, where do we get to? Sked, it was called, yeah. So let's see. Here. So we return back to here. From the scheduler into switch, and then we pop right back out of here. And then where did we come into sked? Well, there was the yield, right? So this is the old process that yielded earlier to the scheduler. Right? We yielded up. We ended up running the scheduler for a while. At some point, the scheduler decides, oh, I'm done here. Let's run this process again. So we switch over, and now we come back out through the sked, through the yield, through our trap, and then eventually trap ret, and then we return back to the user land part of the process. Right? So switching the process is actually all happening inside the kernel. Right? We're going from one process. When we call yield here, eventually we're not running the same process anymore. We're in the kernel. At some point we're in the scheduler. We go back to another process. Maybe we don't even leave the kernel, and we yield again, come back to the same process. So just because you're in supervisor mode, that doesn't mean you're running just the kernel. You're running the kernel on behalf of some process. Right? There's some current process. And at some point, we go back into user space, so the process gets to run its own instructions. There's two kind of context switches here. There's one user mode to supervisor mode, and then there's one inside of the kernel switching between which process we're running on behalf of at the moment. And that's the context switch. All right, we'll do that one more time, I think, on Tuesday. I suggest you take a look at the code. Try to follow this yourself, going in and out of processes. It is a bit, what's it called? Convoluted and crazy. Yeah, this is not something that you do every day. So, okay. Have a good weekend, and I'll see you on Tuesday.